Hi everyone, my name is Naseem Alam, and today I am going to share my capstone project, that is Yulu bike sharing demand prediction. Mm, Yulu is a popular bike sharing service that supports eco-friendly and smart commuting. But one big challenge is knowing how many bikes people will need and where they will need them. In this project, I used data and machine learning to predict bike demand. This helps Yulu plan better, improve customer service, and support sustainable transport. Uh, let's now let's look at the main goals of the project. First, make sure bikes are available when needed. We want to predict demand in different areas, so bikes are where people need them. This helps avoid shortage or unused bike in low demand zones. Second is make customers happy. When bikes are easy to find, users are more satisfied. This means less waiting, more trust, and more people choosing Yulu again. Help the environment. This project also supports clean and green transport. By improving bike availability, more people can switch from cars to bike, which helps reduce pollution. Adjust to changes easily. Things like weather, traffic, or events can affect how people use bikes. With this, with this model, you can prepare ahead and respond to these changes. Fifth one is use data to make a smart decision. Lastly, we use all this data to make better future plans. Advanced models help us predict more accurately and improve services over time. These are the libraries. Uh, I have loaded dataset, and this is the dataset first view. These are the rows and columns. These these are the data info. I have checked missing value. There is no missing value. This is the missing value heat map. Let me now give you a quick overview of the dataset I used. It contains a total of 14 features and near about 9,000 rows, which means we have data for every hour in a year. Out of these 14 features, four are categorical columns such as date, seasons, and functioning day. These are stored as object types and tell us things like the time of year or whether it's working day or not. The remaining 10 columns are numerical and we can divide them into two types based on how they are stored. Uh, Integer columns include rented by count, hour, humidity, visibility, and float columns, temperature, wind speed, dew point temperature, solar radiation, rainfall, and snowfall. Another good uh, another good thing is there are no missing values in the dataset. That means the dataset is already clean and ready for analysis. So we did not have to spend time filling in gaps. Understanding our variables. These are the variable description and these are the our statics. Checking unique values for each variable. Date have 365 unique variables. Rented bike count has 2166. Average 24-hour temperature. These are the unique variables. Season, there are four types of season and two types of holidays. That is holiday or not holiday. Functioning day. While uh, bike are given on the rent. Functioning days are those days when the bikes can be given. Data wrangling. First, we start with rented bike days filtering. To make to make the data more relevant, I first filter the dataset to include only the rows where functioning days is marked as S. This means we are focusing only on days when bikes were actually available for rent and ignoring days when the service was not working. After filtering, the functioning day column becomes the same for all rows. It's always yes. Since it's no longer useful, then I removed it to keep the dataset clean and simple. After this, I separated date and time. After filtering out non-functioning days, the next step was to clean and organize the data further. I removed the functioning days column because it became redundant. All values were the same after filtering. Then I worked on date column. I converted it to date time format and split it into three separate columns: day, month, and year. These help us analyze seasonal and monthly trends more easily. At this stage, I also uh, separated the features into two types: uh, numerical variables and categorical variables. So now the dataset includes only valid functioning days and it combines both numerical and categorical variables or columns. This gives us a strong foundation for meaningful analysis and accurate prediction using machine learning models. Uh, let's start with ADA. After this data wrangling, I draw KDE plot, that is distribution of numerical features. I used KDE plot to see how the numerical features are spread. Most features like temperature, humidity, and hours are fairly normal and symmetric. But features like rainfall, snowfall, and solar radiation are positively skewed and have lots of outliers. This tells that some features might need transformation before modeling, especially those with extreme values. The second chart is rented by count vs date-related variables. I used bar charts to understand how bike rentals change with time. The chart shows that rental bikes are highest at 8 a.m. to 5 p.m., which are rush hour. Weekdays have more rentals than weekends, meaning people mostly use bikes to go to work or school. Spring and summer months, especially April to August, have the most rentals. Winter months see less demand. Also, rental increased in 2018, showing growth in bike usage. These, these insights help to us plan better, like sending more bikes during busy hours or offering promotions in summer. It also shows where we can reduce costs, like during winter or late nights when demand is low. Seasonal distribution of rented bike count. I used a bar chart to see how bike rentals change with seasons. The highest rentals happen in summer, so Yulu should make sure there are enough bikes and maybe run summer promotions. Spring and autumn also have good demands, so it's smart to keep users engaged with offer or events. Winter has the lowest rentals, like due to cold weather. To improve this, we could offer discounts or special deals to attract riders even in winter. These seasonal insights help you plan better, use bike efficiently, and boost business at right time. Rented bike count by holiday. I use both a bar chart and pie chart to compare bike rentals on holiday vs regular days. The bar chart shows the actual counts, and the pie chart gives a quick view of the share. About 96% of rental happen on regular days, showing that most popular people use bike for daily commuting. Only 4% of rentals happen on holidays, which means there there is an opportunity to promote bikes more for leisure. These insights help you to focus on keeping bikes ready for work days, but also plan campaigns to increase holiday usage and avoid unused bike. Hourly patterns by holidays, season, and weekends. To understand hourly bike rental patterns, I use three subplots, each focused on different factors. The first plot showed that on regular days, rentals bikes at 8 a.m. to 6 p.m., which are typical commute hours. But on holidays, the pattern is more relaxed, peaking uh, around 11 a.m., suggesting more leisure use. The second plot com- compares seasons summer. The second plot compares seasons. Summer has the highest rentals, especially during rush hours. In winter, rentals drop and are spread evenly, likely due to the cold. The third plot breaks down weekdays vs weekend. Weekdays shows sharp peak at the commute time, while weekends are more balanced with a small bump around late morning. Now, relationship between temperature and rented bike count. This scatter plot shows how temperature affects bike rentals. We clearly see a positive correlation as the temperature rises, so do the bike rentals. Rentals peak between 20 degrees Celsius and 30 degrees Celsius, which appear to the most comfortable range for biking. Rental drops significantly, very cold, that is less than 0 degrees Celsius, and very hot, that is uh, greater than 35 degrees Celsius. This insight helps the business in several ways. More bags can be made available during warmer months like summer. Targeted promotion can boost rental in ideal temperature range. Bubble chart for rental by temperature and season. This bubble chart shows the relationship between temperature, bike rentals, and season. Each point represents a day. The x-axis is temperature. The bubble size shows how many bikes were rented, and the color indicates the season. We can clearly see that the bike rentals increase between 20 degrees Celsius to 30 degrees Celsius with summer and spring, showing the highest demand. Even at similar temperatures, winter sees fewer rental bikes, likely due to colder conditions affecting user comfort. Autumn, on the other hand, has a stable demand in warmer days, suggesting room for seasonal promotion. These insights help these insights help us optimize operations, target promotions, and plan for demand shift across seasons and temperature. Box plot. This box plot, uh, these box plot helps us. These box plot help us quickly spot outliers and understand how our numerical features are distributed. Outliers like feature rainfall and snowfall shows extreme spikes indicating rare weather events. Humidity has a wide spread showing high variability across the year. Variables like uh, variables like wind speed appear uneven, hinting at possible transformation needed for modeling. These insights help us pre-process data, better handle outliers smartly, and focus on impactful features, all of which lead to better model performance and a smarter business decision. Correlation heat map. This correlation heat map helps us quickly spot a strong relationship between variables. Positive correlation: rented by count increase with temperature and dew point. Warmer weather boost rentals. Hours shows moderate correlation. Demand varies by time of day. Negative correlation: humidity negatively impact visibility and solar radiation. These insights help us select the most impactful feature and avoid multicollinearity in our models. Pair plot. We used a pair plot to explore relationship between multiple variables and bike rentals. Temperature BS versus rentals. Clear positive correlation. Warmer days see more rentals, especially in summer and autumn. Humidity. Rentals peak at moderate to high humidity, particularly in summer. Wind speed. Lower wind speed are linked to higher rentals. Strong winds may discourage biking. Seasonal impact. Rentals are highest in spring, summer, lowest in winter, even with similar conditions. This chart gives us a compact but powerful view of how different factors interact with each other and with rental demand. Let's now move on hypothesis testing, where we used a statistical method to validate patterns we observed in data. First, hypothetical testing is holidays versus non-holidays. Our first hypothesis asked if bike rentals differ between holidays and non-holidays. We used Welch t-test and found a p-value which is far below 0.05. So we reject the null hypothesis, confirming a significant difference. Bike rentals are noticeably lower on holidays. Next, we tested whether rentals differ between summer and winter. Using the same statistical test, we got a p-value of zero point 0.0. So we again reject the null hypothesis. This means uh, this means sees much higher bike usage than winter. Finally, we explored the relationship between temperature and rentals. The Pearson correlation test gave us correlation coefficient of 0.56 and a p-value of zero point 0. This shows moderate positive correlation as temperature rise, bike rentals increase. In summary, our hypothesis testing confirmed what we saw in our visualization. Bike rentals are significantly influenced by holidays, season, and temperatures. Let's now talk about how we handle outliers in dataset. First, we handle missing value. So previously we saw uh, previously we see that there is no missing value in our dataset. Handling outliers. We use various transformation techniques to handle the outliers. First, we should know what is data transformation. The data transformation is the process of converting, cleaning, and extracting data into usable format that can be analyzed to support decision-making process and to propel the growth of an organization. Many features like bike count and weather variables were positively skewed. This skewness can affect model that assume normal distribution. So we tested three transformation techniques. First is log transformation, that is a great for compressing large value but need strictly positive data. A square root transformation, that is a moderate effect, reduce skewness while preserving original structure. Cube root transformation cube root transformation works with both positive and negative values. By visualizing all three side by side, we compare their performance and choose one of the best normalize each variable. To finally, we see uh, to further stabilize variance and reduce skewness, we applied power transformation with the EU Johnson method. Since it handles both positive and negative values, unlike box plots, we applied power transformation on wind speed, solar radiation, rainfall, and snowfall, and also the rented by count. These transformations help make a data more Gaussian-like, which improve model performance and reduce bias from extreme values. After transformation, the data became more suitable for modeling with improved symmetry and reduced outlier impact. Now, let's take a quick look at how power transformation impacted our data distribution. For this, uh, I visualize before and after power transformation. Before power transformation, we visualize the original data set, histogram, and QQ plot. The histogram shows clear skewness, and the QQ plot revealed a strong deviation from normality. After transformation, the histogram became more symmetric, and QQ plots aligned closely with diagonal. indicating data is now more narrowly distributed. Thus, we choose power transformation using the Yo-Yo-Johnson method because it reduces skewness and stabilizes variance. It handles both positive and negative values. Unlike log transformation, this transformation helps improve the performance of the model that assume normality and prevents extreme values from skewing results. After this, to handle categorical data, I use one hot encoding. I applied it to the season and holiday column since they have no natural order. This method creates separate binary columns for each category, making it easy for the model to interpret feature manipulation and selection. To reduce multicollinearity and improve model performance, I analyzed feature correlation. Highly correlated pair like temperature and dew point temperature were simplified by keeping only one. These reduce redundancy and ensure the model is not biased by overlapping information. I also created new feature to capture hidden relationship, boosting predicting power. For feature engineering, I began analyzing correlation with our targeted rented by count. Temperature, hour, and solar radiation shows a strong positive correlation, while winter rainfall and snowfall had negative impacts. Will explain a function that helps us train, test, and evaluate machine learning models. It also creates visualization to make the results easier to understand. Let's go through each step. First step is splitting the data. First, we divide our data set into two parts: train data, that is 80%, and test data, that is 20%. The model learns from the training and is later tested on the test data to see how well it performs. Step 2, scaling the data. Next, we scale the data so that all features are the same range. This is important because some models work better when all values are standardized. Step 3 is training the model. Now we train the machine learning model using the training data. This means the model is learning patterns from the data so it can make prediction. Step 4, making prediction. Once trained, the model make prediction on both the training and test data. This helps us check how well it's performing. Step 5, evaluating the model. We use different metrics to measure the model accuracy such as R square, mean absolute error, and mean square error, as well as root mean square error. Step 6 is visualizing the result. To make it easier to understand, we create graphs, a scatter plot show how close prediction are to actual values, and a line graph helps us see trends in the last 20 predictions. Step 7. Finally, we display a table that compares actual value with predicted values. This helps us see where the model is making mistakes. Data scaling. We used we used an 80-20 data split, 80% for training and 20% for testing. Now, let's look at how we initialize and evaluate multiple machine learning models efficiently using a Python loop. We start by creating dictionary called models, where each key is the name of the regression model, and each value is the corresponding model's object from a machine learning library. This includes linear regression, random forest regression, gradient boosting regression, XGBoost regressor, and LightGBM regressor, decision tree, and support vector regression. All of these are commonly used in regression tasks, especially when predicting continuous outcomes like bike rentals. Before training the model, we also initialize a standard scalar. This scalar standardizes the feature values so that all of them are on a similar scale, which helps improve model performance, especially for models like SBR and gradient boosting. Based on the evaluation metrics, the best four models of hyper tuning are XGBoost, LightGBM, random forest, and gradient boosting. I used randomized search CB to tune the random forest regression because it is faster and more efficient than grid search CB. After tuning the model, the train R square dropped from 99 to 96 and R square remained strong 0.91, showing that overfitting has reduced. While the test RMSM is slightly increased, this trade-off worth it because the model now generalizes better to unseen data. So overall tuning helped us build a more balanced and reliable random forest model. We tuned gradient boosting regressor using hypermeter optimization and saw a major performance boost. R square improved 89 to 94. We used two we used two hypermeter optimization technique for XCB boost. First randomized search CB for a quick performance baseline, followed by Optuna, which perform a more efficient and targeted search. After tuning with Optuna, we saw clear improvement. More accurate for the light GBM regressor, we applied hypermeter tuning using randomized search CB. On training set, the R square value was 95 and the mean square error was 0.0506. These results indicate that the model is performing consistently well on both seen and unseen data, which means low overfitting and good generalization. From a business perspective, this means our predictions are highly reliable, accurate forecasting leads to better resource planning, cost efficient, and improved decision making. Final model selection. Out of all models we tested, the gradient boosting regressor tuned using randomized search CB gave the best balance of accuracy and generalization. It achieves R square of 0.94 and low RMSE, which was better than both random forest and XGB boost tuned with randomized search. Even a tough XGB boost with Optuna had slightly higher performance. We choose gradient boosting because it offers more consistent result without overfitting and is easier to interpret and deploy in our case. That's why gradient boosting is our final model. It's stable, powerful, and generalized well to unseen data. Feature importance and model expandability. Our strong correlation due to commute times, future work and deployment optional. As a part of future work deployment readiness, I as a part future works and deployment readiness, I focused on two key tasks: model saving and performing a sanity check with unseen data. First, I saved the First, I saved the best performing model, which is the gradient boosting regressor, along with the power transformation object used during preprocessing. This is essential for deploying the model to a live environment where we can reuse it without retraining. After this, we check on unseen data. This data mimics that what a real user might send the model with features like our temperature, humidity. Predictions were made on transform scale and finally inverse transform back to the original rented by count scale for real world interpretation. This confirmed that entire pipeline from model conclusion and business impact. The core the core objective of this project was develop a machine learning model that predict bike rented demand using factors like time, season, and weather. This helps bike rented companies improve operations, increase revenue, and enhance customer satisfaction. Key solution and business impact. Our model predicts rental demand accurately based on hours, season, and weather conditions. This enables proper bike availability during rush hours, avoiding shortage and low revenue. A smarter distribution across high demand locations. Weather-based pricing and promotion. We found clear patterns between weather and rental business can now use dynamic pricing like discount during low demand days, run seasonal campa- campaigns, boost usage in winter or rainy weather, operational effect, efficiency and cost action. With demand forecasting, companies can avoid wasting resources on underutilized bike, schedule staff more efficiently, lower maintenance and operational cost. Our insights help create personalized promotion, targeted target weekend riders for leisure campaigns, focus weekday marketing on commuters, enhancing user experience. The model supports real-time updates on bike availability, which reduce wait times, improves overall convenience, keeps customers happy and uh, coming back. Model performance. We evaluated several models, including XGBoost, LightGBM, random forest, and gradient boosting, using both randomized search and Optuna for hypermeter tuning. The final model we chose was gradient boosting, tuned with randomized search because it has a high test R square that is 94 and low RMSE, better generalization and less overfitting compared to others. Final conclusion. This project achieved its goal. We built a powerful and reliable demand forecasting system that can directly improve revenue through a smarter demand prediction, reduce cost by optimizing operations, deliver a better customer experience with real-time planning, and uh, give business a competitive edge through data-driven decisions. In short, this machine learning solution has the potential to transform how bike rentals business operate, helping them scale efficiently and serve customer better. And that brings us to end of this machine learning capstone project. We successfully built a bike rental demand prediction model that not only improves business operations but also enhance customer satisfaction through a smart data-driven insight. Thank you for watching, and I will see you in the next one.